Hello everyone, in this video, which is part 2 of looking at adaptations to hot and cold climates, what I'm going to talk about is something called surface area to volume ratio. That's really important because let's take a cold climate for example, in a cold climate, if you're trying to conserve heat, the last thing you're going to want to do is lose heat through your body, through your surface. So by working out the amount of surface you expose per unit volume, we can sort of learn more about the organisms and whether they would or are more likely to lose heat or not. So we're going to talk about surface area to volume ratio. Now, when I do this topic with my students, I tend to ask them to think about a polar bear versus the squirrel. Two very different animals, two very different habitats. One very, very large animal, polar bear, one very small. And then I say to them, which one is likely to lose heat quicker? And just off the size alone, most students will say the polar bear. But we're going to prove today that that is actually incorrect, and that the smaller the organism, the more likely it is to lose heat through diffusion. And we can show this by thinking of three very simple cubes. So I'm just going to sketch here 3 cubes, each one a little bigger than the last. Not the best drawn cubes, but still. And we're going to imagine each side is in centimetres. I'm not going to include any units in this. Normally, obviously you would. So like an area, for example, would be in centimetres squared, volume centimetre cube. We're just going to look at the actual physical numbers. We're imagining this first cube has a length, width and diameter of 1 centimetre cube. Let's imagine this second cube has dimensions of 2, 2 and 2. And finally the length, width and depth of this bottom cube is 3 by 3 by 3. So clearly in this, the large animal, the polar bear, is represented by the big cube, and the smaller creature, the squirrel, is represented by the small cube, the 1 by 1 by 1. So what we're going to do is first of all look at surface area. So we're going to consider the surface area of these 3 cubes. Now, surface area is length times height, and as it's a cube, so there's 6 sides, we need to times that up by 6. So if you work out the surface area of the 1 by 1 by 1, that would come out as 6 centimetres cubed. The 2 by 2 by 2 would be 2, which is 4. Lots of 6, that would be 24. And equally 3 by 3 and then times 6 would come out as 54. 3 by 3 is 9, times 6 is 54. Now we need to look at volume. So we need to try and consider what the volume of these 3 cubes would be. Now the volume would be the length times width times the height. So again, for the smaller cube, we get a volume of 1. For the 2 by 2 by 2 cube, if you work that out, that would come out as 8. And 3 by 3 by 3 has a volume of 27 centimetre cubed. So now finally what we want is the surface area to volume ratio. And you work out the surface area to volume ratio, so that's what we're looking for now, this one here, by ultimately dividing that surface area by the volume and expressing it as we said, a ratio. So if we did that, the top cube would give us a ratio of 6 to 1. Now, we ideally want the volume to 1 because we're looking per volume, per centimetre cubed. And we're going to try and see how much surface area is exposed per volume. So we get a ratio of 6 to 1 at the top, cube 2 by 2 by 2. The ratio can be simplified down there as 3 to 1, and 54 and 27 will give us a ratio of 2 to 1. Now what that ultimately means is, if we notice that the volumes are all 1, so per volume of cube, the smaller that you are, the more surface area you expose. So you can see, for every 1 volume, if you like, at the top, we expose 6 surface area, whereas for every 1 volume of the larger cube, we're only exposing 2. And the large cube represents the large animal, so in this case the polar bear. So clearly the larger creature is only exposing 2 surface area, if you like, per volume, less surface area. So there is less opportunity for heat to diffuse. Fick said that diffusion rate was proportional to the surface area times concentration gradient divided by diffusion distance. So clearly, if you expose more surface area in an environment, there's a greater chance that heat would be lost more. You'd lose more heat through a bigger surface. That's common sense. And we can see that being smaller, we're exposing more surface for our given volume. So even though you're a lot smaller, you actually have more surface area exposed for every volume that makes you up. So you're more likely to lose heat quicker. Which is ideal because in a cold environment, you're not going to want to be able to lose your heat very quickly. You're going to try and conserve that heat. So that's just a little bit about surface area to volume ratio and why it relates to this adaptation topic. Now, one thing which is a little bit silly perhaps, but I show this to my students just to get the point across again, and I'm just going to show it on this video here. And I talk about the man with the large face, and I talk about the man with the small face. It sounds very silly, but I want you to imagine that I place this square on their face. We're going to look at how much surface is exposed in that square. So we're keeping volume of that square the same. So if I were to place it on this man here, it would look something like that. And if I place it on this man here, it would look something like that. Now I'm hoping that you can see that this square represents the unit of volume, but on the large face we only have a very small area of skin exposed. Yet on the smaller face, representing the small cube or the smaller creature, for that given volume, much more of its surface, much more of that face is within that cube. So exposing more of its surface in that volume. It's a bit of an unusual way to show it, but I find that helps some of my students to explain the relevance of surface area to volume ratio. Okay, so I hope all of that helps.